For today's lesson, we are going to be discussing how to do proofs that have a disjunction, as well as what are known as existence and uniqueness proofs. And so these are sections 3.5 and 3.6 of our textbook, respectively. Now, in the section for existence and uniqueness, I'm going to do a couple of results that are proven in the textbook, as well as an additional result that actually will harken back to our early days of our math education. So namely, the existence and uniqueness of remainders. So we know that when we divide a number such as 13 by 4, the remainder is 1. And we are instilled that that remainder is unique. And so the goal today is to prove that. But in addition, we will see another aspect of how induction can be used that is not the proofs that we did for homework or in the lesson on induction. Namely, we are not going to be proving a formula, but rather we're going to be using the technique that we have a statement P of n for every natural number n, and then proving that this gives the remainder to be exist and be unique. And so that is the goal for today. So to get started, let us consider the following proposition that we proved back in 3.1. So what it says is the product of two odd integers is odd. In 3.1 we proved this, but we did it directly. And I made a comment that we could do this by the contrapositive, but we did not have the techniques yet. And so the goal for today, one of the goals for today, is to discuss how one does a proof that has a disjunction. Because if we apply the contrapositive to this statement, since we have an AND statement, so of course, here we have P, M and N are odd integers, and we have Q, Mn is odd. So when we do the contrapositive, this becomes not Q, which is Mn is even. But then for the not P, now here, this is going to become by De Morgan's law. M is not odd, or N is not odd. Said differently, M is an even integer, or N is an even integer. And so, just to put it formally here, what we have is that the contrapositive states that if M and N are integers, if Mn is even, then M is even, or N is odd. And so we want to prove a statement that now has a conclusion that has a disjunction. And so now, if we were to formally view this in the following ways, we have P implies Q or R. To prove such a statement, because we have that Q is either true or false, we have two options. If Q is true, then we are done, as that will show that this here is a true statement. If Q is true. Now, if Q is false, then we show that R is true. And then we're done. And so the key idea here, when proving a statement like this, is that we may assume that Q is true, and we get one case for free. And so the other case that remains is a situation when Q is false, and then we show that then R must also hold. I mean, that R must hold, since that would imply, that would give that the implication is in fact a true statement. So for example, if we were to do our scratch work here, we are going to take as our givens that we're going to take P, so we have Mn is even, and we're going to take also that M is odd, and so this is the not Q. And then our goal is to show that then N must be even. Okay, so how do we use these? So both of the givens, the fact that Mn is even, by definition, that tells us that there is some integer out there. Let's go ahead and call it k, such that mn is equal to 2 times k. M is odd, by definition, is equivalent to the existence of some integer, let's go ahead and call it L, such that m is equal to 2L plus 1. So now, if we put these together, we have that m times n is equal to 2k, which is the same as also saying 2L plus 1, where here now this is m, times n. If we expand the right-hand side, we have 2L times n plus n. But now we have an equation. 2k is equal to 2ln plus n, so we can solve for n. And solving for n will give us 2k minus 2l times n, which allows us to factor out a 2, and we now have k minus l times n. But to be even is to have 2 times some integer, and that's exactly what we have. And so we have shown that n is even, and that is our proof. So now let's go ahead and write this formally. So we've gone ahead and gotten started. So we're proceeding by the contrapositive. So we are going to suppose that m times n is even, so that there is some integer k such that m times n is equal to 2k. Now, so observe that if m is even, then there is nothing to show. So suppose that m is odd. Then there is an integer L such that m is equal to 2L plus 1. And now we do the argument we just did. Consequently, we have m times n, which is equal to 2k, and then we go through just write everything we did in the scratch work. And so now we have 2k equals 2ln plus n. And thus n is even. And we are done. We are now done with the proof, and we have the contrapositive here. And so the main takeaway for the contrapositive in this disjunction is that because we can take the case when m is even for granted for one situation, we only have to do the case when it's not even. And that finishes the proof. We are done. Next, we're going to prove the following theorem, which is covered in the book. Now, in this case, if we look at our givens, we have that A is a subset of C. We have that B is a subset of C. And so, of course, here A, B, C are sets. So we're given this. And then we want to prove that A union B is a subset of C. Now, we know that this statement has the form for all x is in A union B, implies that x is in C. And so with what we discussed last time, we can go ahead and replace the goal. Because we can go ahead and take an arbitrary element, x, in A union B. Since what we want to prove is an implication, we just have to take some arbitrary element in the union of A and B and show that that x itself is in C. And so we can go ahead, replace the goal with just X is in C. And so that's what we want to do. But in doing so, by taking this arbitrary element in the union of A and B, we don't know where that element is. For example, if we have our Venn diagram, where we have our two sets, so let's say that the red set is B, the blue set is A, then where is that X? It could be here, just in A, it could be in the intersection, or it could be in B, but not in A. Well, the key thing is, we can go about just assuming that X is in A for one case, and X is in B for the other case, and do it in that manner. And so that's the way we are going to do this. So what we are going to do here for this statement is two cases. Case 1, X is in A. Case 2, X is in B. Because in both of these, that will exhaust all the possibilities. That's all we can take, since we know it's in the union. We know it's going to be in A, or it's going to be in B. If it happens to be in the intersection, that will not play a role for us. And so we use this information. So for case 1, we have these here, and X is in A, and then the given tells us that since A is a subset of C, then X in A has to be an element of C. And then similarly, if we look at X is in B, we will have that X has to be in C. And so we will also be done in this case. So let's go ahead and prove this and see how the formal write-up looks. So suppose A is a subset of C, B is a subset of C, and X is in the union of A and B. We now proceed by cases. And so case 1, now we go ahead and take X to be in A. Then X is in C, since A is a subset of C, and we're done. And then case 2, we go ahead, let X be in B, then X is in C, since B is a subset of C, and we are done in this case. And in both cases, now we have shown that if X is in the union of A and B, then X is going to be in C in both cases. And so now we can just conclude, hence, X is in C in both cases, which shows that A union B is a subset of C. And we're done. So let us do a more involved example. So now, once again, we have A, B, and C are sets, but now the goal is to show this containment here. So goal, we want to show that A minus B, and then parentheses, minus C, is a subset of A minus B union C. Well, if we use a definition for this, we know that this here will be for something of the form for all X. X is in A minus B minus C, implies X is in A minus B union C. And so we can restate the approach as taking some X in A minus B minus C, and we want to show that then that X is in A minus B union C. But now, if we go ahead and expand, so now we're going to start off the proof formally. So if we expand by the definition, So we have the set difference here. So by definition of the set difference, this is the same as saying x is in A and x is not in B minus C. Okay, so we have that. But now, to not be in B minus C, that's a set difference. So the definition here is x is in B, so for B minus C, we know that this here is the set of x's such that x is in B and x is not in C. So if we were not to be in B minus C, that means that x cannot be in B or x is in C. And so we can go ahead and write that in here. And so we have x is not in B. So again, we are negating the definition of what it means to be inside the set B minus C. And that tells us, by De Morgan's law, that x is not in B or x is in C. Now, if we use the distributive law, we can go ahead and see that these here is logically equivalent to x is in A and x is not in B or x is in A and x is in C. So at the end, what we end up getting for the statement that we want to prove is that in wanting to show this goal, our assumption, our given, is actually a statement of the form P or Q. And so we want to have P or Q implies an R, where R is this statement here. And so that's how this looks in its logical form when we expand the given statement. And so this is just as in the previous statement. In the previous case, we had a statement of the form P or Q, and we had our two cases, case 1 and 2. And we consider those separately. And so we are going to do the same thing in the proof here. So we're going to have a case 1, where we're going to go ahead, assume that x is in A, and x is not in B. So if we assume this, we want to show that then x is in A minus B or C. But now, this here, by definition, this is equivalent to the set that x to be for x being in a set difference A minus B. And so we have that x is definitely in the union. And so that takes care of case 1. If we look at, say, case 2, now we want to assume the second statement, Q, which we have x is in A and x is in C. And so in particular, we have that x is in C, and thus x is in the union of C with A minus B. And so we are done in this case as well. So now we have everything to do a formal proof of this. And so let's write the formal proof. So we choose an arbitrary x in the set difference A minus B minus C. So in particular, we have that x is in A and x is not in B minus C. Now observe that x is not in B minus C is equivalent to x in B or x is not in B or x is in C. And so now one thing here about the write-up is that I am saying this part over here that x is not in B minus C, that it is equivalent, which we did in the scratch work. And so something that is now going to be different than what we have done in the previous material for the course is that in our scratch work we went about explicitly showing that statement. So we went through x is not in B minus C, we recalled the definition, and then deduce that this was equivalent to X is not in B or X is in C. But since this is going to follow from the definition, now this is one aspect where we can jump from this statement to this statement, as it is a matter of just circling through the definition to deduce that X not in B minus C is the same as X is not in B or X is in C. And so we can make this logical jump and just say here that these are equivalent. And so now, with that, we have our assumption. So we have X is in A, and X is not in B, or X is in C. And so now we have two cases. The X is in A is always going to be with us, but now we have the two cases, X is not in B, or X is in C. And so we can go ahead and now proceed by cases. So we now proceed by cases. So case 1, let's suppose that X is not in B. Since X is in A, we have that X is in A minus B, and thus X is in A minus B union C, and we are done. And so we can just end right there. We have shown what we wanted. And so here now we have case 2. We do the same thing. So now we're going to suppose that X is in C. Now, we once again, so in this case we don't need to use the fact that X is in A, but we can again go ahead and say, so suppose X is in C, so that X is in A minus B union C. In both cases, so from the two cases above, we conclude that A minus B minus C is a subset of A minus B union C. And so we can now conclude the proof here. And so something to note here, when we were writing the scratch work, I made the separation where we did the distributive law and we had X is in A and X is not in B. Whereas in the proof, I did not say the step, but instead kept working with this. And the idea is that we already know that X is in A. And so we really just have to consider the cases X is not in B and X is in C separately. And that's what we have done, since we already know that X is in A. So we don't have to go through and say, suppose X is in A and X is not in B. Suppose X is in A and X is in C. We are using that implicitly since we already know that X is in A from the start. So our next topic is the notion of a proof, an existence and uniqueness proof. And so we use the symbol. So we have our there exists and then an exclamation mark X, P of X. And this is going to mean that there is exactly one X such that P of X holds. So how can we write this in a logical form? So we can go ahead and write this as there exists X such that P of X, and so that tells us the existence. And now the uniqueness. So here's the existence portion. And then for the uniqueness, we have for all Y and for all Z. If P of Y and P of Z hold, then it is the case that Y is the same as Z. And so now we have that since we have our X here, such that P of X holds to be true, and then this implication here is telling us that if P of Y is true for some Y, it must be the same as the X that we have here. And so that's how we define the long form for this here. And so we have there exists exactly one X, so that P of X is true. Now, in the textbook, the following theorem is proven, and I'm not going to go through the proof of this in today's video, but please read the proof of the theorem. And so what it says is that each of these three logical forms are equivalent. And so it goes through the proof. What I want to focus instead is on actually showcasing how a proof that does existence and uniqueness goes. And so the one comment I will say on the proof of the theorem, since we have not discussed proofs where you want to show the equivalence of several statements. So the way that this is proven is, as we saw with the biconditional, if we have an if and only if, let me just write on the right side over here. So we have an if and only if, we first prove one direction, and then you prove the second direction. With a proof of the form, the following are equivalent, we would prove first 1 implies 2, then we prove 2 implies 3, and then you prove that 3 implies 1. And by doing that, then we have that 2 is equivalent. So we see 2 also 1, since we can go from 2 to 3 and then 3 to 1. And so now we have 2 if and only if 1, 2 if and only if 3, 3 if and only if 1, once everything is done. Now, the way we want to interpret these statements is as follows. So the first one is telling us that there exists an x, so that we have p of x, and then for every y that's such that p of y is true, then this implies that y is equal to x. And so that's just as you will see in the book, it's just a rephrasing of the logical form for this one here, which is case 3. And then of course we have number 2, which is telling us there exists an x, such that for all y, p of y is true if and only if y is equal to x. So let's see how we actually do proofs like these. So there is a unique set A, such that for every set B, A union B is equal to B. Well, we want to prove that there is exactly one, so we come back to the forms here. So now, how do we use this? So in this case, we want to show that there exists a set A that is unique for every single set B. So for the proof, the goal that we want to establish based on the logical form for there exists exactly one A such that this here holds, we first need to establish the existence portion. And so this side here. So for the existence, we want to find a set A such that for every set B, it is the case that A union B is equal to B. And then we want to show the uniqueness. And so again, this is the existence portion, and this is the uniqueness portion. Now, the way that we're going to go about uniqueness is by choosing another set. And so suppose that there was some set out there. Let's go ahead and call it C. So suppose that there exists a C such that C union B is equal to B for every set B. We want to then show that A is equal to B. Because the idea is, have it backwards, that A is equal to C. And so the idea here is that we're choosing some C so that C union B is exactly B. But we already know that we already have a set A above. The key thing is, we're supposing that there is a C, but this C is chosen arbitrarily, and so we're choosing some set C that satisfies this. And what we are showing is, the moment that we have this equality for every set B, then it must be the case that A and C are the same. So for this proof, the first thing we need to do is find a set A that we know works for every B. So what's an example of that? So pause the video, give this some thought. What is an example of a set A that will satisfy A union B is equal to B for every set B? And so, one possible set is the empty set. And of course, if we assume the conclusion, we know that this will be the unique set. But we have here, so scratch work. So we know that the empty set union B is equal to B for every set B. And now for uniqueness. And so that's it. We're done with existence here. We have already shown that there is some set. So next, for uniqueness, let C union B equal B for each set B. So for all B. Let's suppose that this is the case. But now, what we want to do is show that C is equal to the empty set. So how can we do that? Well, we are assuming this statement here to hold true for every single set B. And so we can use that to our advantage. Because here, we're working with some arbitrary B. But we just have to choose one B that works nicely and show that this is the case. So what if we choose B to be the empty set? So in particular, we have that C union the empty set is equal to the empty set. So here we are thinking about the empty set as the one possible B above. And so by assumption, we have that C union B is equal to the empty set. But now, we know that C union in the empty set. So since C union the empty set is equal to C, we must have that C is exactly equal to the empty set. And we've established the uniqueness. And so that's the key in this situation, is that by assuming uniqueness, we have that this is true for any choice B, for any set B that we desire. And so we do have that clever aspect that we had to employ here, where we chose the empty set to be the set to do this on. Now, in the book, they also prove the theorem in a similar way, but they use two different sets C and D, and use that C union D is equal to D union C to then conclude the uniqueness. And so I leave it to you to also compare with the proof in the book, which gives a alternate proof for this. So let's go ahead and formally write the proof of this theorem. So proof, I'm going to write the proofs here slightly different in the book. The book, as with induction, it separates them into, say, an existence and then the uniqueness portion. Perfectly valid. I just want to provide an alternate way of also doing the same writing. And so we want to prove there is a unique set A, so that for every set B, A union B is equal to B. So let's go ahead and let B be any set. Then, if we take the empty set, union B, we get back B, which establishes the existence portion of the proof. Of the proof. So now we go towards uniqueness. So next, suppose that C is a set such that C union B is equal to B for each set B. Now we do the argument that we did in just earlier, where now we take B to be the empty set, since this holds for every set B. So in particular, we have that C union the empty set is equal to the empty set. And now, since C union the empty set is equal to C, we conclude that C is equal to the empty set, which establishes uniqueness. And so we are done. Now if you compare this proof with the one given in the book, they're slightly different when it comes to uniqueness, but both are perfectly valid. In terms of writing, Bellman does start off the proof by saying existence here and then uniqueness here, whereas we have opted to go ahead and write existence portion in the proof that we have established it, and then we have established the uniqueness. So both are perfectly correct ways of writing a existence and uniqueness proof. So for the next theorem, we want to prove that for each real number x, if x is not equal to 2, then there is a unique real number y, such that 2y over y plus 1 is equal to x. So let's do the scratch work for this. In this case, establishing existence is rather easy, because we just need to find a y in terms of x. So for existence, write y in terms of x. And so for example, if we go through, we have 2y is equal to x over y plus 1. And so we can go ahead, bring the y over to the other side upon expanding. So we're going to have y and then the 2. If we expand here, we have xy plus x. If we subtract the xy over, we're going to have 2y minus xy. And so we're going to have a 2 minus x here is equal to x, which then tells us that then we can write y as x over 2 minus x. But now x is not equal to 2, so we can of course divide. So this is valid, since x does not equal to 2. And so this is crucial. This assumption is crucial because if x was equal to 2, then we cannot do what we just did, because we will be dividing by 0. And so that assumption is necessary. And so we have existence. We have that for every single x, we can define y to be x over 2 minus x. And then this here will hold true. What about uniqueness? So for uniqueness, suppose that there exists some real number z such that 2z over z plus 1 is equal to x. And so now what we are going to do is show that z is equal to y. And so here we want to now show that z is exactly equal to y. But if we do the same thing that we just did over here, so we write 2z is equal to x times y times z plus 1, we solve for z, we are going to get that z is equal to x over 2 minus x. So then, so we can go ahead, skip the steps here, we're going to get that z is equal to x over 2 minus x by the same procedure above, which will show that this here is exactly y, since we got that from the existence portion. So therefore, z must be equal to y. Now, if we want to write this proof formally, we can go ahead, let x be a real number, such that x is not equal to 2. As we saw with our last lesson, for the existence portion, all we have to do is then claim the y. And so we're going to go ahead, say take this y here and work backwards. Choose y and then show that this here holds true. So now let y be equal to x over 2 minus x. And here, just to mention, note that y is a real number since x is not equal to 2. Next, we go through and reverse the process. So observe that we can start with y is equal to x over 2 minus x. We can multiply both sides by 2 minus x. So now we have y is equal to, 2y. Expand out, we have 2y minus xy is equal to x. We can go ahead, bring the xy over to the other side, and we have x plus xy, which we can then factor out in x, and we have 1 plus y. And finally, we get back that we have 2y over 1 plus y is equal to x. Now, over here I wrote if and only ifs along the way, since each of these procedures are reversible. We can go from here to here, and then similarly for this. So all these expressions are essentially the same in that we can use the methods in algebra to go back and forth between them. And so we have our x. And so now we have established the existence portion. For uniqueness, we're going to suppose that there is some z. Such that 2z over z plus 1 is equal to x. Now we can go through and do the same argument that we did in our scratch work here and conclude. And so what I'm going to do is, I'm just going to skip that argument. So show computation. And conclude z is equal to x over 2 minus x, which is equal to y. And that will finish the proof once we fill in the computation doing it in reverse. So next, let us have a brief discussion on the division theorem. I am taking back what I said at the start of the video since we are already close to the 45-minute mark. I will not be proving the division theorem in today's video, but rather at the beginning of our next lesson. So the division theorem is another result that dates back to antiquity, 300 BCE. It appeared in Euclid's The Elements. And what it says is, if a and b are positive integers, then there exist unique integers q and r, such that a is equal to bq plus r, where 0 is less than or equal to r, and r is strictly less than b. We call r the remainder. So for example, if we were to take 4 divides 13, and here I'm using the method in the United States, this varies from country to country. But in the US, with the method, if we wanted to do this division, we will go ahead and say 4 goes into 13 3 times, so we have 4 times 3 is 12. Subtract these, we get back 1, and now that's our remainder. But another way we can interpret this is that 4 times 3 plus 1 is equal to 13. And so now we have 13 is equal to 4 times 3 plus 1. And so now in the abstract notation of the division theorem, we have that 13 is our A, our 4 is B, 3 is Q, and R is 1. And so Q is referred to as the quotient. And so what we want to do is prove that the quotient and the remainder are always unique. And the proof that we are going to do at the start of our next lesson relies on induction. So specifically, we're going to be looking at the following statement. If a is a positive integer, we are going to let s of a be the statement for each positive integer b, there exist integers q and r such that a is equal to bq plus r. Now, the thing about the proof is that it is induction, but it's not an induction argument in the way that we introduced in our previous video when we discussed induction. We're not proving a formula, but now we're doing this in this statement here and showing that this statement S of A is true for every positive integer a. And then the principle of mathematical induction will then say if we prove by induction that S of A is true for all a, we then establish the existence portion of the proof. But the argument that we will do is a lot of symbol pushing, which if we do not do an explicit example, it is easy to miss out what is going on. And so what I am going to do to finish it off for today is do an example, a concrete example where we can see how the inductive step occurs. So for example, let us take A to be 58 and B to be 3. Then what we end up getting is that 58 is equal to 3 times 19 plus 1. And so if this is the case for our S of A, we want to consider how do we get the Q and the R for 59 with B being 3. So here's essentially the inductive step in this very concrete example. So if A is equal to 59 and B is equal to 3, how can we recover Q and R from 58 equals 3 times 19 plus 1. And so here's the idea. We add 1 to both sides. And so now we have 59 is equal to 3 times 19 plus 2. And in this case, we are done because we have B. Our Q is now 19, our R is 2, and in this case, there is no problem. So we are done. But notice that we have two cases. It's not always going to go this way. Because if now we decided to do, say, 60, and continuing B equals to 3, so for 60, we need to do some work. And so then we'll have 60, we add 1 to both sides again, and we're going to have 60 is equal to 3 times 19, but now we have plus 3. And now we have a problem, because the remainder, since our B is equal to 3, the remainder has to be at most 3. But now we have that's equal to 3, so we need to do some manipulation. And so what we do then is factor out a 3. So we factor out a 3, we have 3 times 19 plus 1. And so now we get that this here is 3 times 20, and now we know what our Q is, and the remainder in this case becomes 0. And so when we do induction, we are going to do the same exact thing that we just did for this computation with 58, 59, and 60. But because we're going to be doing everything in symbols, we will have to consider two different cases. The case when our R is not equal to B minus 1. And the case when R is less than B minus 1. And so we're going to be doing this same argument, but all with symbols. But the main thing is, the idea that's going to happen is exactly what we just did, just replacing everything with a symbol, and we're going to be able to get our induction proof at the beginning of our next lesson.